Welcome once again to our lecture series on introduction to computer and CSC 102. And we are looking at problem solving tools. In our first class, we handled abstractions and the different types of abstractions as a problem solving tool. And today we are going to be looking at algorithms. My name is Engineer Sahon Kuro, and I'll be taking you through some of what algorithm is all about. So just pick up your jotting pen and jot all the points that I have to say. In computer science, an algorithm is a step-by-step procedure or set of instructions designed to solve a specific problem or perform a particular task. It is a precise and unambiguous set of rules that can be followed to accomplish a desired computation or operation. Algorithms can be thought of as a recipe or a blueprint that guides a computer or a program on how to solve a problem. They take inputs, perform series of well-defined operations or computations, and produce an output or a solution. Good algorithms are typically designed to be efficient, reliable, and correct. So efficiency refers to the algorithm's ability to solve the problem using a reasonable amount of time and resources. While reliability may likely mean that reliability means the algorithm is consistently produces, or the algorithm consistently produces the correct output for all valid inputs. So, and lastly, correctness ensures that the algorithm solves the problem according to its specification. When I said that the algorithm is referred good if it is efficient, reliable, and correct. So, algorithms can be expressed in various forms, such as pseudocodes. They can be expressed in flow charts or even a programming language. They serve as a fundamental building block for computer programs and play a crucial role in various areas of computer science, including data structures, sorting, searching, graph algorithms, machine learning, and cryptography, among others. So the first thing I'm going to be looking at here is the characteristics of what an algorithm is. The first characteristic that an algorithm has is that it is well defined. An algorithm must have a clear and unambiguous set of instructions, leaving no room for interpretation. For example, to be well defined, it means that its steps and instructions are clear, precise, and unambiguous. Each step should be explicitly defined and leave no room for interpretations or confusion. The algorithm's behavior should be deterministic, meaning that given the same input, it should always produce the same output. Being well defined ensures that the algorithm can be executed correctly and consistently by a computer or a program. It allows different people or systems to implement the algorithm in the same way and achieve the same results. So to demonstrate the well-defined nature of an algorithm, it is often helpful to provide detailed specification, including the expected input format, the expected output format, and the specific operation or computations to be performed at each step. These specifications should be precise enough to avoid any ambiguity or misunderstanding. Additionally, being well defined also implies that the algorithm covers all possible cases and inputs, provided a solution or input for, or rather providing a solution or output for each scenario. It should handle both base cases and general cases, ensuring that it works correctly for all inputs within the core problems domain. So in conclusion, a well-defined algorithm is essentially for clarity, precision, and reliability, enabling efficient implementation across different. So another characteristics of an algorithm is that it is finite. We say that an algorithm is finite. That means that it must terminate after a few, for an algorithm to be after a few number of steps or any given unit or enter an infinite loop. Finite algorithms have a well-defined ending point where they produce the discipline. The algorithm's execution should eventually reach this termination point, allowing the problem or the computer to proceed to the next task or exit gracefully. So the finiteness property is crucial because it ensures that the algorithm is timed. So execution, making it impracticable or unusable. So it's worth noting that the termination of an algorithm does not necessarily mean it has to be fast or efficient. An algorithm can have a high time complexity and still be considered finite as long as it eventually terminates for all inputs. When design algorithms, it is important to consider the termination condition and ensure that there are no loops or recursive calls that may lead to infinite loops. Proper design and implementation practices along with careful consideration of the algorithm's logic can help ensure the finiteness property. Let me say that again. A proper design and implementation practice, along with careful considerations of the algorithm's logic, can help ensure the finiteness property. So that's another characteristics of an algorithm. The third characteristics of an algorithm is it is executable. An algorithm should be implementable and executable using a computing device, executable and run algorithm can be machine instructions that people to algorithm to is that it should be well defined, unambiguous steps to instructions that can be translated into a code. Each step should be precisely defined, leaving no room for interpretation. Then the second thing is that computational operations. The algorithm should consist of operations or computations that are computationally feasible. This means that each is available resources and capabilities. And the third thing to look at if for an algorithm to be executable is that it should be supported by a programming language that the computer understands. This language could be a high-level language like the Python language, like an assembly language. You understand? So, and the third property that it should be well defined. The second is and the third is that it should be supported by programming languages translatable to machine instructions. Meaning that the algorithm in the chosen programming language should be translated into machine instructions that the computer's processor can execute. The translation can be done through compilation or in the programming language. It will follow the algorithm steps and output of solution. The executable characteristics as it allows programs to be applied practically to. Now, another it is deterministic, the same output. To say that an algorithm is deterministic means that it will, regardless of how many times it is executed, in order with the same initial conditions, it will constantly yield the same output. So determinism is in algorithms is crucial because it ensures reliability, predictability, and repeatability. It allows different users or systems to obtain the same result when desirable in consistent behavior and faster editor by performing inputs that would lead to different outcomes each time it is executed. However, it is important to note that determinism applies necessarily to different external, while overall outcome user input, random number algorithm is one inputs and execution. In an algorithm is precise unambiguously for confusions when an implement step should be well defined exactly to be performed. Requirements, output expected consistently by different programmers or same among developers and ensures that the algorithm behaves as intended in various scenarios. So preciseness also plays a crucial role in the analysis and evaluation of algorithms. It enables the calculation of time and space complexities as well as ability to reason about the algorithm's correctness and efficiency. So to ensure precision in an algorithm, it is often beneficial to use formalized notations like pseudocodes or flowcharts. These notations help clarify the sequence of steps, conditions, making the algorithm's implementation and execution more precise. So in conclusion, precision in an algorithm is vital to application and reasoning about the algorithm. That will now take us to a simpler way of reading in case if we are being asked an example. So what I did here was that I came up with programs. So in case if you have been asked for the character fed programs, that is refers to finite characteristics, executable characteristics, and deterministic characteristics. Then the program itself represents precise. So with fed programs, you can be able to know the different characteristics of an algorithm. We're going to read them. So we ended our class with algorithm analysis, where we looked at efficiency and told us that for us to analyze an algorithm, we need to look at its efficiency and how to measure it, the time complexity, space complexity, and big O notation. Because these are very key terms that you will need to really understand. You will need to really understand. I decided to make the time complexity and space complexity into different videos, and then we're going to start with the efficiency. Please take note that when we're looking at algorithm analysis and we're looking at efficiency, we should always know that algorithms can be evaluated in terms of their efficiency, which refers to how quickly they can produce the desired output. When analyzing an algorithm's efficiency, it involves evaluating how well it performs in terms of time and space requirements. The goal is to understand the algorithm's resource usage and determine how it scales with input size. There are some examples out there for analyzing an algorithm's efficiency. One of the key examples is the time complexity analysis, which we will look into in our next video. This actually involves determining how the algorithm executes, how the algorithm's execution time grows as the input size increases. It actually focuses on identifying the dominant operations or steps and expressing their growth rates using the big O notation or other asymptotic notations. Time complexity actually, or rather, time complexity analysis provides an estimate of the algorithm's efficiency in terms of time. So that's just one. The second one is the space complexity analysis, which this actually involves the amount of memory or space required by the algorithm to solve a problem. It considers factors such as variable storage, data structures, caution depth, similar to that. These are the variables that it considers. Similar to time complexity is space complexity. In the sense that it's also expressed using big O notation or other notations. Space analysis helps assess the algorithm's efficiency in terms of memory usage. Then we also have the best case, worst case, and the average case analysis. The algorithms may have different performance characteristics based on the input they receive. For best case analysis, it determines the minimum time or space required for an algorithm to solve a problem, while the worst case analysis identifies the maximum time or space required, while the average actually considers the expected performance average for a random input distribution, maybe looking at optimism and rest. Then the last one, I think, or rather another way of another analysis we look at is the asymptotic analysis. This focuses on understanding the algorithm's behavior as the input size grows to infinity. It allows for generalizing the algorithm's efficiency by ignoring the constant factors and focusing on the most significant terms. Asymptotic analysis provides the high level. We can also look at analyzing algorithms through empirical analysis. In addition to the theoretical analysis, and the empirical analysis actually involves running the algorithm on real-world data or synthetic test cases to measure its performance. This approach helps validate and refine the theoretical analysis, taking into account real-world factors such as hardware, software, and specific input distributions. By analyzing an algorithm's efficiency, we we kind of compare different algorithms for the same problem, identifying bottlenecks, make information. When we identify the bottlenecks, uh, it also make information informed decision, informed design choices, and it also helps to select the appropriate algorithm for a specific use case. So we are going to be looking at the time complexity. Okay, let's look at time complexity and how to relate it to algorithm analysis. Time complexity of an algorithm measures the amount of time required by an algorithm to run. Typically, in terms of input size, you need to take note of that. In terms of the input size, so time complexity is a measure of the amount of time an algorithm takes to run as a function of the input size. It helps us to understand how the algorithms and performance scales as the input grows larger. Time complexity is typically expressed using big O notation, which describes the upper bound or the worst case time complexity. So let's look at a few examples to understand the time complexity. Now, in a situation where we have a constant time complexity, it's usually expressed in this format. This is the big O that we're talking about, or rather the order, and this is the input, which is a constant. Now, an algorithm with a constant time complexity takes the same amount of time to run, regardless of the input size. It has a constant number of operations. For example, where we have this code function print first element in the array, or rather of this is the input ARR of the other variable, and it's declared as an array when we are printing it out. It's no matter how large the array ARR is, the algorithm will always perform a single operation, that is accessing the first letter and complete in constant time. Now, let's look at the linear time complexity. It's written in this order, and n is the input. So an algorithm with a linear time complexity has a running time that grows linearly with the input size. It means the number of operations is directly proportional to the input size. For example, let's look at this code where we have function print, just the same code, but this time around, we're having a for loop there. Yeah, the algorithm needs to iterate through each element of the array, ARR. Yeah, it iterates through each element of the array, ARR, and performs a constant time operation, which is to print. As the array grows, the number of operations grows proportionally. That's the difference in this case. Now, let's look at another example. We have the product time complexity, where the input is raised to power 2, or the squared input. So, an algorithm with quadratic time complexity has a running time that grows quadratically with the input size. It means that the number of operations is proportional to the square of the input. Like in this example we're looking at this place now. In this algorithm, for each element in I, for each of the elements I, in the array ARR, it iterates again over all elements J and performs a constant time operation to the print. So as the array size increases, the number of operations grow quadratically. It's a quadratic time complexity. Now let's look at a logarithmic time complexity, where the input is a log of n. So an algorithm with a logarithmic time complexity has a running time that grows logarithmically with the input size. It means that the number of operations decreases as the input size increases. So let's say, for example, we have the function binary, declare the function, and we initialize the variable low, and also initialize this with the main function. The binary search is an example. The binary search is an example of an algorithm with a logarithmic time complexity. It repeatedly divides the search space in half, reducing it logarithmically as proposed. So as the size of the input array doubles, the number of operations increases by a constant factor, not linear. So these are just a few examples of just to illustrate different time complexities that we have out there. It's important to note that time complexity analysis focuses on the dominant term and the overall growth rates of the algorithms and running time, ignoring constant factors and lower order terms.
Now, the next thing that we also look at is the space complexity. Now, space complexity is a measure of the amount of memory or space required by an algorithm to solve a problem as a function of the input side. It helps us to understand how the algorithm's memory usage scales as the input grows larger. So space complexity is also typically expressed using the big O notation, time complexity later on. Now, describing the upper bound or the worst case complexity. So let's explore some examples to understand space complexity. We have the constant space complexity, which is 0, 1, and in this case now it's a constant. So an algorithm with a constant space complexity uses a fixed amount of memory, regardless of the input size. It means that the space usage does not depend on the size of the input. For example, let's look at this code where we have two variables and we're adding it up. Now, in this algorithm, the space usage is constant. It uses a few variables, the A, B, and C, that occupy a fixed amount of memory, regardless of the value of A, and whether the mathematical value just uses a fixed amount of memory. Now, let's look at the linear space complexity, where we have the input of n. Now, an algorithm with a linear space complexity uses an amount of memory that grows linearly with the input size. The space usage increases proportionally as the input grows larger. For example, let's look at this code where we have a function find max, and then we have declared a variable with the array. In this algorithm, we have an input array, ARR, and the algorithm rates through the array to find the maximum value. It uses a constant amount of additional memory, which is called a max bar. That's the additional memory to store the current maximum. Okay? Now, as the array size n increases, the space usage also grows linearly. That's how it is. As it increases, it grows linearly. Now, let's look at another example, which is the quadratic space complexity. In this case, an algorithm with a quadratic space complexity uses a memory allocation that grows quadratically with the input size. As this is the input size now, it grows quadratically. The space usage increases proportionally to the square of the input size. Let's take, for example, now, where we also declare a function n. Now, in this algorithm now, we generated a matrix size of n by n, and then the algorithm requires memory to store each element in the matrix. To store each element in the matrix. And then as n increases, the total space required grows quadratically. And you can see as it increases, the space grows quadratically. That's what this code is all about. Now, let's take another example where we look at the logarithmic space complexity, where the input is log of n. Now, an algorithm with logarithmic space complexity uses a memory allocation that grows logarithmically with the input size. The space usage decreases as the input size increases. Technical that the space usage decreases as the input size increases. So let's look at the code where we can understand that treatment very well. We have a function as well for the binary search, and it's supposed to divide the binary search. The algorithm operates on a socket array ARR, and then repeatedly divides the search space in half. In this case, the target is search space, which is divided in half repeatedly through the while code. Now, so it requires a few variables, which is the low, the high, and the mid. The low, the high, and the mid. What happens here is that it uses the variables to store the indices. So as the input size grows, as the input size n, as it grows, the space usage does not increase linearly, but rather logarithmically. Now, these examples illustrate different space complexities, showcasing how the space usage of an algorithm can vary based on the problem and the algorithm's design. So space complexity analysis helps evaluate memory requirements and can guide optimization efforts to reduce memory consumption.
And this time around, I want us to look at the term big O notation. We are trying to look at how an algorithm is being analyzed. So let's not forget that as our goal. So what I want us to look at in this session is the big O notation. Big O notation is a mathematical notation used to describe the upper bound and the worst case performance of an algorithm in terms of time and space. In terms of time or space and complexity. Now, it provides a way to express how the resource requirement of an algorithm grows as the input size increases. So, in big O notation, the letter O represents the order of rows or the complexity. It is followed by a function that represents the relationship between the size and then the number of operations or the
the amount of space used. It's often denoted as N, as you can see in there, it's denoted as N. So we have the big O and then the N denoting the number of the relationship rather between the input size and the number of operations or amount of space used. Now we are going to be looking at some common notations used in big O. The first, as you see, is referred to as the constant time complexity. This notation indicates that the algorithm's time or space requirements remain constant regardless of the input size. It means that the algorithm takes the same amount of time or uses the same amount of space regardless of how large the input is. Now, the second notation we should look at is the linear time complexity. Now, in this case, this notation denotes that the algorithm's time or space requirements, the algorithm's time or space requirements grow linearly with the input size. It means that the algorithm's performance is directly proportional to the input size. So as the input size doubles, the number of operations or space usage also doubles. You understand? Now let's look at the third notation, which is the logarithmic time complexity. This notation signifies that algorithms' time or space requirements grow logarithmically with the input size. Sorry, I don't know why I cannot pronounce this very well. It is logarithmically. Okay, it just shows that it grows with the input size in that context. It means that the algorithm's performance improves as the input size increases. So as the input size doubles, the number of operations or space usage increases by a constant factor, not linear this time around. Now, the fourth is the quadratic. So that's the function now raised to power 2. These notations indicate that the algorithm's time or space requirements grow quadratically with the input size. It means that the performance of the algorithm is proportional to the square of the input size. So as the input size doubles, the number of operations or space usage quadruples. That's what it just means. It just quadruples the number of operations or space usage. And there are others. These are the common ones we often that as a result of this lecture we'll be looking at most of our examples. But there are others that you can also look at. We have the cubic time complexity, and we also have the exponential time complexity. So in general, the big O notation provides a concise and standardized way to describe an algorithm's performance. If you are looking at the performance of the algorithm or the performance characteristics, allowing for easy comparison of algorithms and analysis. So it helps in evaluating the scalability and efficiency of algorithms, guiding the selection of appropriate algorithms for specific use case. So if you are looking at what kind of algorithm to use on a particular use case, these are how